Okay, so let me. Okay, hi, my name is Gianluca, and this talk is called Everything is a Device. It's based on my current project, which is a personal project, and yeah, the subtitle gives you an idea to my style of developing this project. Anyway, so who am I? I am a programmer mostly. I currently work in a company which is in stealth mode, which is called Zidida, back in Santa Clara. I personally live in London. In the past, I worked for random companies, some good, some bad. And in the open source world, I've mostly been affiliated with the Minix3, the GNU Hard, and the Xen. As you can see, essentially, hypervisor and operating system is what I've also been working mostly in my life. So the things about me is that I create a lot of personal projects. So, and mostly I do it for fun. I don't really think about getting like the next big thing. I just like to learn new stuff. I just need to satisfy my curiosity. And yes, I need to have fun. And this is one of my personal projects. It's not curiosity in the sense that it's my first kernel that I write. It's one of my old hobbies. So, but anyway, that's what we're going to talk about. Anyway, the outline of this talk is the following. So, I'm first going to introduce MH and MSG. So I already introduced MH in the FOSDEM on 2016, but for people who are not there, it's going to be interesting. Is there going to be another introduction? Also, things have changed since then. Then I'm going to explain the kernel architecture to explain better how I create such system. And then I'm going to speak about something which got me excited very recently, which is the RAM kernel, and usually using the kernel components of NetBSD inside MLG, inside the user space, and also running unikernels in such a system, and how easy it is to take anything and run a unikernel on it. It's very interesting. Finally, if you have time, a conclusion and then Q&A. So I like questions, so in case you want, and I'm not offended if somebody interrupts me, so in case you have a question, just feel free to ask me anytime. Okay, this is an introduction to MLG. So what is it? Okay, so as you can guess by this room, it's a microkernel. Its name is Mojang, you can read why. And yeah, so this has been essentially a background personal project of me. I never had a full-time investment in it. And I actually started in 2015. In 2016, I introduced it at FOSDEM in this dev room. Then on mid-2016, for randomish, for complex issue, I had to put the project on hold. That could start working on late 2017. And so I've been working since back and forth because I started a new job, so things have been very hectic. But the 5 minutes a week I work on this project, and this is about what I got, what I achieved, and what we can do about it. So why MH? There are mostly three reasons. The first reason is that when I started, I really wanted to build a system. So I realized that like with modern system, with modern Linux, especially, oh no, I cannot rant about Linux on desktop, sorry. Anyway, with modern Linux, I lost control of the machine. The things I like about Linux at the old times is that when you boot it, you see your computer. I lost control of what my machine is, what the hardware look like. And this is what I wanted. I wanted a system that I can boot in it, I can play with the device, I can play with the hardware, I can poke it, I can see what hardware I own, which of course like with modern Intel architecture is very hard anyway, but at least we try. And then I also wanted to experiment with software. And it's fun to create modular systems, to create a system that interacts with hardware, but you can actually also start to do random things. They use hardware in a different way. Repeat, it's experiment. I use the word experiment, but actually mean fun. And yes, it's actually nice to try something relatively different because it cannot be completely different because it's going to be a kernel, it's going to be a user space, it's going to be a libc. It's the same thing over and over again, but you change something and you look interesting. And yeah, it's quite fun, to be honest. One of the things which was unexpected when I started this project, it's really fun to see the expression of my friends, especially the one who understands about the operating system, when I tell them that I'm building a system where everything is a device. It's really fun, how the strange look of disappointment and questioning that they have. It's really fun. And so actually, this is the energy to which I'm continuing this project. So what is the MH architecture? The MH architecture is that everything is a device. So what does it mean? Well, it means that like the physical hardware that is present in the kernel is actually exposed in the user space as a device, but also all kernel services, for example, the timer or anything with the console and office, the thing that come on the top of my mind, that is also exposed to the user space as a device. And the process exposed, for example, like mapping a kernel is like talking to a memory controller. And then, you know, a process itself, another process can become can actually become a device. And it would be really, well, you can guess if it's a process user space device or not, but the fact that it creates a non-hierarchical element in a system, it's nice, because yes, it can be dangerous, but I don't care. I'm here for the fun. And so essentially I'm creating a parallel system, a system where like I can experiment things. And you know, there's no way I can actually create a user space that behaves exactly like an hardware device. And you know, that's exactly what people are trying to do now with QEMU and other things. So it's okay. The interface itself for the microkernel is very low level. And I like that. So essentially, when I connect to a device, essentially I see a bus with device attached to it. Of course, it's a bit different because I need to open the device, there's a JIT, a UID, etc., etc. And like, the memory is lower, especially when you map the memory like you're speaking to a memory controller, and then you're going to receive page fault, and then you need to react to that. And when you fork, for example, the kernel is not going to copy and write magically the page. You're just going to receive a pages fault which tell you, you're trying to write to a shared page, fix it now. And so it's the kernel which need to copy the memory. I like it. And then, you know, we have the sysbus-cal interface. Essentially, the way I interact to a device is to very low-level system. So, for example, I have IRQs. And each device has IOMMUs. In order for the device to write to my memory, I need to export memory to the IOMMU. And I have IO ports because I like x86, and it's very impossible to simulate memory map anyway. So once I have this system that can essentially substitute what the file system is in Unix, I left the rest very Unix-ish. As I said before, I had fork. That's why I don't use something which is much more typical in microkernel, like capabilities and fine-grained resource control. I don't care about that. I want to have fun. And it's much easier to build a system like this. It's much funner because the nice thing about Unix is to help you doing this. So this is an example to what I mean. And this is a magic way of slide reusal, because this is my 2016 presentation. So this is what the process sees. This is how the process interacts with the world. The user space process, in order to interact with another device, can program the IOMMU, and the IOMMU can write to this memory. And the device is trying to send to my IRQs, and I'm going to map the IRQs into signals. And then I can send essentially IO ports. So, oh, hello. This is essentially what the kernel looks like. But honestly, like as I said, I have a very low-level system. So the question is another one. The question is, how do I use it in a sane way? Because I don't really want to handle page fault anyway. And that's why I essentially enters MRG. MRG is essentially like the runtime library, which essentially creates some interface and essentially some basic primitives. It was meant essentially initially just to handle the virtual memory, but then I started adding the fiber and event handling and memory management. And interestingly, I started to have the need to create device drivers for the device that I connect to. So essentially I start to have library device driver inside MRG. And this is essentially what it is. MRG is a set of basic library. I'm creating a system which runs in the same address space and some device driver that can run. And this device driver can be device driver for real hardware, like for fake hardware. And yeah, and then what else he has? He has bootstrap server and a console, which is quite interesting. But essentially, the bootstrap server is the first process that starts and that enumerates the devices. I will tell you in the next slide how it does that, because it's quite interesting. And yeah, this is what it is. So this is the slide about the kernel architecture. It's a single slide, but I think it's quite interesting. So the way it works is this. Like, as you can see, like the part about the scheduler, the CPU, the memory management, the PMAP, and the physical CPUs is relatively traditional. Repeat, I do some weird stuff on fork because I don't really have copy and write. I just protect the shared pages. But it's relatively traditional. What is interesting is the rest of the kernel, which takes even on code-wise, the majority of the thing, which is the device handling system. And the way it works is that you got the system bus. And what the system bus does essentially, like every call in which I interact with a device, go to the system bus. The system bus has essentially attached all the registers, all the devices attached to the system, like probably a file system essentially, but with VFS essentially. And what happens when I do that is that then inside the kernel there are three or four types of devices that can attach to it. And the one I want to start for is the platform device. So essentially the platform device starts at the beginning And as you can see, it talks directly with the hardware platform. The platform device is a device that exports I/O ports, I/O memory, and I/O memory and I/O queues, but of the whole system. So essentially, if you own the platform device, you can essentially speak to the hardware, whatever the port is. And this is what Bootstrap does. What Bootstrap does at the beginning, opens platform. And then the current Bootstrap has actually ICP-ICA, and then actually it enumerates, it turns on in user space ICP-ICA, and enumerate devices. And what it does then, it creates these hardware devices. Hardware devices are exactly like the platform device, except it restricts the access to only the resources of a single device. So for example, an example we'll see later, if we found the PCI entry 00020, which is the VGA usually, which is VGA compatible, what you get is you get a device for the VGA. What is cute, which I like, is actually I get the ACPI names for the devices, which give me a closer relationship with the guys who wrote the ACPI BIOS, which is nice. And anyway, so what I do essentially, I create all these devices, and it's nice because then I can actually assign devices to a single process more naturally than, for example, an hypervisor does. And it gets quite interesting because then I can actually also list the devices and can know easily what things are. And this is exactly what I want from this system. And yeah, so then what we have, the system device is interesting. I told you essentially is a device which is fixed for all processes. It contains also the timers and the work clock timer and the virtual timer. But what's interesting is this one. So this is how I implement user space devices. So every time a process interacts with asks the system bus for a bus read or a bus write or something, it passes to a user device if it's a user device. A user device just forward the codes to the user space. And so even internally, it's the mechanism and the internal API used for the user device is the same used for the other one. Anyway, this tells exactly what I just told you. And this is where it gets fun. So the problem is this, like just let me think of it. Essentially, like I'm pretty sure that everyone in this room knows about RAM kernels, but what essentially they did was they create components of the NetBSD kernel and the NetBSD system in general. And then they create a way to merge these components together. And it's quite fun. And what I was interesting when I started looking at it is essentially I wanted the file system and the network drivers and the network stack because I want to use somebody else's code on these things. And what I found, and that's amazing, is that actually porting the RAM kernel to your system is really, really easy because what they do, they have this component system. So the things you're going to fight is the make files, but it's okay. It's a plague of humanity we haven't solved yet. So what essentially do, they have this component which is called librampuser, and essentially what you do it's actually it's very POSIXy, but it's easy to port to other architecture. And to me, it took me like 1 day to port librampuser to what I call librampmrg. And when I got that, I immediately saw, it just compiled, the code just compiled, and so just by calling rampinit, I saw, the copyright of the NetBSD kernel, which was beautiful. And it was fun, and I could see that the NetBSD kernel was booting as a library. And then I actually added the component xt4fs. Did I say correct? xt4fs? Yes. And then I start calling mount a device, and because I have my own library ACI driver as a library. So I mounted it. And actually I could use in a kernel that doesn't have a shell, doesn't have any decent code, it's just been hacked out 5 minutes a week for the past 2 years, except for 1 year and a half, which I couldn't. And I can actually get xt4, HCI, and it's really fun. I feel like I'm doing something with my life, despite I'm not. It's amazing. It's really cool. Anyway. So yeah, and there's clearly some love between me, RAM kernel, and MRG, because what essentially happened is that the fundamental things where my system unexpectedly is close to RAM kernels is when, how can I say, like, what I need, since I have like another space and everything is a device driver around me, I need device driver. And since I'm a process, I need library device drivers. And that's what I was creating in MRG. Turns out that's exactly what the RAM kernel gives me. And it's amazing because then I can actually do that. I can actually even use the PCI device. And that's more complicated because I need to port a component called libPCI utils, but can be done. It's beautiful. And yes, and then, okay, this is like me rambling about Makefiles, so don't look. But yes, I can have network drivers as well. And it's very interesting to me. And what I like is that one is very convenient for me, but also it fits very well with my architecture, which was unexpected when I started, so especially when I had the idea in the pub, and I was drunk, by the way. This is the second part, because this is actually a work in process, a product in progress, because it's I just got it running 2 days ago. So, and it was, again, very easy, unexpectedly easy. So what is it? This is not the ramp kernel, this is ramp run. So ramp run are unikernels, and what essentially ramp run is a complete build of the, sorry, what did I say? Yeah, of a complete build of the ramp kernel, and it has also tools to create like images based on that. When I saw ramp run, I say, oh, that's easy, I can just use librampmrg, but it turns out not, because in order to run, it needs its own implementation of libramp users. So what libramp run does is actually creates an interface called BMK, and that's what you need to implement. It's actually much more low level. It's much more close to the real hardware. Like it looks more like the paravirtualized interface for such. It's quite strange. But anyway, that's what it does. And then actually the nice thing is that there's this repository called ramp run packages that already had a lot of ready-made unikernels. Like I had big things like MySQL, Apache 2, Nginx, and MPG123, and we'll see that. So this is fun because then I say, okay, it must be hard to port. And what was really, really hard this time is the fact that like the toolchain that I use in MH was incompatible somehow with the expectation of the linker of the Makefile script, and I wasted one night on that. But it's okay. So what was interesting then, I actually said, okay, let's port ramp run MRG. After fighting with Makefiles a lot, actually creating the BMK interface was really, really, really easy. And again, it took me 2 days, of which, and then a couple of sleepless nights for the Makefile, but it was actually really easy. And what I did when I created ramp run bake, and I decided to take MPG123, which is a M-file file. It just gave me a binary, which is an ELF binary for my MH. So okay, let's boot that. So I put that instead of the bootstrap, and I booted into MPG123. So I don't have no shell or anything, but I do have an MP3 player. And with this, I actually conclude what I wanted to say, because as you can see, like the goal of the system being fun has clearly been met, and it's really fun, and I still don't know how much weird stuff I can do with it, and I like it. Yeah, so essentially, like the things that really struck me and I'm really excited about is that in a system like this, I can actually make MH essentially a unikernel runner, and that's to me really interesting because it will make my project cool, because unikernels are cool. And okay, of course, there's a lot of things to do. And all the code is online. It's all BSD licensed. I'm very tempted by GPL3, by the way, but for now I'll keep it BSD. And it's a bit scattered because it's my project, and I am a bit scattered as a person in general. So the code is there. Please use it. Please have a look at it if you're interested. Please port ramp kernels to your microkernel now. And yes, the code is there. So if you have any problem with finding the code or anything, just ask me. And any questions? This is where you find more information about it. Question, hi.
So does the system require IOMMU to actually import it?
No, it's a security concern, which as you can see, since this is my project and I'm not getting paid to do, I don't really care too much. So, sorry. The question was, does the system require IOMMU to run? So in order to be secure when you assign an hardware, essentially when you program the actual MMU in the, here essentially, let me try to go back. So here, when you actually program the IMMU of the device, if the device is hardware, in a nice world, you should actually find which MMU, in which MMU bus the device is sitting and program. I don't have the code for that. It can be added because actually I have implemented the IOV locator already, so it's just a matter of doing it, of having a device for the MMU. So it's thinkable, I don't. Right now, what you do is what you do when you assign device to your microkernel with other MMU. You need to trust the driver, the device.
I have a question.
Go.
You mentioned networking device drivers
Yeah.
taken from the kernel. Do you already use something like that? Do you use, and if so, did you have any problems with removing the device driver from the rest of the USB networking stack?
No, I have not.
Can you repeat the question?
Okay. Okay, that was a thing. That is to check if I actually listened to the questions. Okay. So essentially the question is, and the answer is no, spoiler alert. You mentioned networking. Have you ever tried the networking of the NetBSD? And if so, of the ramp kernel, so have you had problem disaggregating the network stack with the driver? So no, I haven't, mostly because I need to implement libpci util, and I wanted to do it in a cleaner way, because otherwise I cannot access the PCI drivers. And two, honestly, I don't plan into writing my own stack, so hopefully it's not going to be a problem. But no, I never had. But I think that it would be nice if there was an interest in ramp kernel in people that are using it for microkernels to actually try to do that. That would be interesting. But no, this ramp kernel stuff is like 1 week old, and I'm very excited and jumping up and down essentially. So. Okay. Well, so there was a thank you page.